I will discuss today quantum models of atomic structure. In a 1901 lecture at the Sorbonne in Paris, Perrin proposed an atomic model consisting of a positively charged central nucleus surrounded by a number of electrons to compensate for the central charge. In J.J. Thomson's 1903 plum cake model, on the other hand, the hydrogen atom was a positively charged sphere of uniform density and a radius about 10 to the power minus 8 centimeters, with a negatively charged electron oscillating at its center. But this model failed to account for the large scattering angles in the scattering of alpha particles in experiments that were performed by Rutherford students Geiger and Marsden. The experiments showed scattering angles of over 130 degrees, and this could not be explained by J.J. Thomson's model. In December 1903, Nagaoka proposed his Saturnian model in an address to the Physico-Mathematical Society of Tokyo, wherein the positively charged central nucleus of Perrin's model is surrounded by a number of equidistant electrons revolving around it with a common angular velocity, like the bodies in the rings of Saturn. On March 10, 1910, 3 years before Bohr, Arthur Eric Haas proposed his model of the hydrogen atom in a proposal submitted to the Viennese Academy of Sciences for his habilitation as Privatdozent at the Universität Wien. For those who are unfamiliar with the German and Austrian system, the habilitation is a teaching certificate. Before you can get a teaching appointment at a university, you need to submit another thesis, post-PhD, and pass an oral examination, which is called the habilitation. And the Privatdozent is the equivalent of a lecturer position. In Haas's model, an electron of mass m and charge minus e moves along a circle of radius r, concentric with a uniformly distributed positive charge E in a sphere of radius a. He showed that the atom attains its maximum energy E squared by a at r equal to a, and obtained the expressions which were not very different from Bohr's. But Haas's model was roundly criticized and ridiculed and rejected. Ernst Lescher, director of the Institute for Physics at the University of Wien, called it a joke. Hasselnoll said that Haas's jumbling up of unrelated subjects such as quantum theory, which was then regarded as a theory of heat, and spectroscopy, which was then regarded as a branch of optics, was naive and should not be taken seriously. Haas's application was rejected, and it was only in 1912, after publication of another paper on Thomson's model of the atom, that Haas finally passed his habilitation and secured his appointment as Privatdozent. But as we will see, that's what Bohr did just a few years later, namely connect quantum theory to spectroscopy, although with a completely different model. The distinctive, but first we need to take a brief detour into spectroscopy. The distinctive spectra of many elements with discrete spectral lines had been known for several decades. You might remember the flame tests that you might have done in school or in your undergraduate studies, where each element, each salt has a distinctive color. Sodium has a golden yellow color, copper has a blue flame, barium gives green flashes, and so on. So these distinctive colors had been known for several decades. In 1868, Ångström, in English we write that as angstrom, with a little circle at the above, but in Swedish that A with a circle above is pronounced as O. So Ångström published an extensive catalogue in 1868 of the wavelengths of the lines that he had measured in solar spectra. In 1871, Stoney and Reynolds discovered relations between 4 of the spectral lines of hydrogen, which were catalogued by Ångström. Stoney pointed out that, in his words, it is convenient to refer to the positions of all lines in the spectrum to a scale of reciprocals of the wavelength. which he called the wave number, and this is still in use today. Similar regularities were observed by Liebing and Dewar in the emission spectra of sodium and potassium. A statistical analysis performed by Arthur Schuster showed that such regularities were unlikely to occur by mere chance, and they thus pointed to the existence of some as yet unknown law governing them. Let us now take a trip to Switzerland to visit a Bohr schoolteacher named Johann Jakob Balmer in Basel. Balmer was known to dabble in numerology, and while chatting with a scientist friend one day, he complained that he had run out of things to do. Whereupon the friend replied, "Well, you are interested in numbers. Why don't you see what you can make of the set of numbers that come from the spectrum of hydrogen?" Balmer observed that the wavelengths of the 4 spectral lines measured by Ångström could be expressed as constant times 9 by 5, constant times 4/3 or 16 by 12, constant times 25 by 21, and constant times 9 by 8 or 36 by 32. Notice that the numerators here form the sequence 3 squared, 4 squared, 5 squared, and 6 squared, while the denominators form the sequence 3 squared minus 2 squared, 4 squared minus 2 squared, 5 squared minus 2 squared, and 6 squared minus 2 squared. In 1885, Balmer published his findings in the Verhandlungen der Naturforschenden Gesellschaft in Basel, Proceedings of the Scientific Society of Basel, as the formula lambda equals 3645.6 into 10 to the power minus 7 millimeters times m squared by m squared minus 2 squared, with m taking the values 3, 4, 5, and 6. He also predicted the existence of a fifth line in the spectrum with m equal to 7 and wavelength equals 3969.65 into 10 to the power minus 7 millimeters. Upon being informed that such a spectral line and others had indeed been observed by Huggins, Balmer published a second notice in the Verhandlungen der Naturforschenden Gesellschaft in Basel, showing that his formula applied to all 12 then known spectral lines of hydrogen. This discovery produced a lot of excitement and inspired many studies, leading to the discovery of other spectral regularities. In 1890, Rydberg observed in the Transactions of the Royal Swedish Academy that in the spectra of all the elements analyzed so far, there are series of rays whose wavelengths or wave numbers are functions of consecutive integral numbers. As stated by Ritz, the frequency of every spectral line of an element can be expressed as the difference between two spectral terms, each of which contains an integer. The Rydberg-Ritz formula can be written as 1 upon lambda equals r into 1 upon n2 squared minus 1 upon n1 squared, where n1 and n2 are integers, and r is now known as Rydberg's constant. Or in terms of the frequency, nu equals rc times 1 upon n2 squared minus 1 upon n1 squared, where c is the velocity of light. This finding cannot be explained by classical mechanics, and it calls for a new atomic model, to which we now return. By May 1911, Rutherford had refuted J.J. Thomson's 1903 plum cake model in favor of the nuclear atom model, with a nucleus whose charge is equal and opposite to that of the electrons and whose mass is very large in comparison to the electronic mass. And this model was consistent with the large angle scattering data. Niels Bohr was working in J.J. Thomson's laboratory in Cambridge at the time, but due to a disagreement with Thomson's plum cake model, Thomson politely suggested that it might be nice if he, Bohr, left Cambridge and went to work with Rutherford. Accordingly, Bohr left Cambridge in March 1912 to join Rutherford's group in Manchester. He soon realized that the stability of the Rutherford atom could not be reconciled with the principles of Newtonian mechanics and Maxwell's electrodynamics, because these would lead to radiative dissipation of energy accompanied by a steady contraction of the atom. That is, the atom would emit radiation and the electron would lose energy and spiral into the nucleus. Bohr sought the solution to the stability problem in Planck's quantum of action, and postulating that there exists a discrete set of permissible or stationary orbits, and as long as the electron remains in one of these stationary orbits, no energy will be radiated. Well, what would be the radius of such an orbit? Note that the dimensions of action are energy times time. Thus, h squared by me squared has the dimensions of length. In his 1913 philosophical magazine paper, Bohr actually provided 3 different derivations of his formula for the energy of a hydrogen atom. I think this is typical of Bohr's thoroughness. I'll outline only one of them here. In Bohr's model of the hydrogen atom, for an electron in a circular orbit, the balance between the centripetal force and the force of attraction leads to this equation, and rearranging this equation then leads to the following expression for the angular velocity omega. Now Bohr imposed the quantization condition E equals half nh omega, leading to Bohr's energy formula E equals minus 2 pi squared m e to the power 4 by n squared h squared. Bohr then provided a simple interpretation of his quantization condition in terms of the angular momentum L equals mvr, which can be written as 2 pi m omega r squared, and this can be written as half m into 2 pi omega r whole squared by pi omega, which, when we recognize that v equals 2 pi omega r, works out as half mv squared by pi omega, or E by pi omega. So then the quantization condition E equals half nh omega becomes E equals pi omega L. Therefore, it's equivalent to the angular momentum quantization condition L equals nh by 2 pi, or the angular momentum has to be an integral multiple of Planck's constant divided by 2 pi. As Bohr said, the angular momentum of the electron around the nucleus in a stationary state of the system is equal to an entire multiple of a universal value independent of the charge on the nucleus. Okay. So we can state Bohr's assumptions can then be stated as: number 1, energy radiation is not emitted or absorbed in the continuous way assumed in the ordinary electrodynamics, but only during the passing of the systems between different stationary states. Number 2, the dynamical equilibrium of the system in the stationary states is governed by the ordinary laws of mechanics, while these laws do not hold for the passing of the system between different stationary states. Number 3, the radiation emitted during the transition of the systems between two stationary states is homogeneous, and the relation between the frequency n and the total amount of energy emitted is given by E equals h nu. Number 4, the different stationary states of a simple system consisting of an electron rotating around a positive nucleus are determined by the condition that the ratio between the total energy and the frequency of revolution of the electron is an entire multiple of half h. Assuming that the orbit of the electron is circular, this assumption is equivalent with the assumption that the angular momentum of the electron around the nucleus is equal to an entire multiple of h by 2 pi. Number 5, the permanent state of any atomic system is determined by the condition that the angular momentum of every electron around the center of its orbit is equal to h by 2 pi. We can now define. For simplicity, we now cast Bohr's formula in atomic units by defining the atomic unit of mass as the electronic mass as equal to 1, the atomic unit of charge, that is the electronic charge, which is equal to 1. The atomic unit of action is Planck's constant by 2 pi, which is set equal to 1. And using these, the Bohr's energy formula in atomic units, that is by putting m equal to 1, E equal to 1, h by 2 pi equal to 1 for atomic number z, works out as En is equal to minus z squared by 2n squared. So with this energy formula, we have for a transition from stationary state n1 to stationary state n2, the difference of energy, which will be equal to the energy of the radiation emitted, is equal to minus half z squared into 1 upon n2 squared minus 1 upon n1 squared, which has to be equal to hc by lambda. Compare this with the Rayleigh-Ritz formula. C by lambda equals Rc into 1 upon n2 squared minus 1 upon n1 squared. So using this formula, Bohr was able to calculate a numerical value of the Rydberg constant R. Okay. So Bohr's formula leads to the Rayleigh-Ritz formula and to all the lines in the emission spectrum known thus far, and also to new lines that would be discovered later. So for instance, if we have these are the energy levels, and using Bohr's formula, these are the energies. So for transitions from n1 equals 2, 3, 4, 5, 6 to n2 equal to 1, we have the Lyman series, which was discovered in 1914. For n1 equals 3, 4, 5, 6, and 7 onwards to n2 equals 2, we have the Bohr series, which we have already talked about, which was discovered in 1885. For n1 equals 4, 5, 6, 7, 8 to n equal to 3, we have the Paschen series, which was discovered in 1908. For n1 equals 5, 6, 7, 8 onwards to n2 equals 4, we have the Brackett series, which was discovered only in 1922. And finally, the Pfund series, which was discovered in 1924 as arising from transitions from n1 equals 6, 7, 8 to n2 equals 5. Bohr's attention was then drawn to a paper published by the American astronomer Pickering in 1886, who claimed to have found additional hydrogen lines with wavelengths 3814, 3857, 3923, 4028, 4203, and 4505, and which were not accounted for in Bohr's formula in this, and these were observed by Pickering in the spectrum of the star Zeta Puppis. Rydberg accounted for these lines with the formula nu equal to Rc times 1 upon 2 squared minus 1 upon m plus half squared, and nu equals Rc into 1 upon 1.5 squared minus 1 upon m squared, with m equal to 2, 3, etc. But Bohr reinterpreted these spectra and showed that Rydberg's formula could be rewritten as nu equals 4Rc into 1 upon 4 squared minus 1 upon k squared, where k equal to 2m plus 1, which is equal to 5, 7, etc. And nu equal to 4Rc into 1 upon 3 squared minus 1 upon k squared, with k equal to 2m, which is equal to 4, 6, etc. And thus that these lines originated not from hydrogen, but from ionized helium, that is helium plus, with a nuclear charge of 2 electrons. Okay. And thus, with this formula, and this was confirmed experimentally by Evans, but Fowler pointed out that a small 0.04% discrepancy between the observed wavelength and their theoretical values. Bohr then pointed out that this discrepancy was resolved when one accounted for the finite ratio of the electronic to nuclear masses and used the reduced mass, mu equals mass of the electron times mass of the nucleus divided by mass of the electron plus mass of the nucleus, instead of the electronic mass, in his energy formula. Thus En equal to minus 2 pi squared z squared mu e to the power 4 by n squared h squared. Okay. And this formula accounted for the discrepancy and was also subsequently used by Urey and his team in their discovery of the isotope of hydrogen, that is deuterium, in 1932, by observing the isotope shift in the hydrogen spectrum. Bohr's theory of the hydrogen atom was well received It aroused considerable interest and spurred intense activity in the field for the next decade. Einstein described it as an enormous achievement and one of the greatest discoveries. But in spite of its remarkable successes, it is important to point out that Bohr's theory gives the right answer for the wrong reasons. For Bohr's theory works only for hydrogen and hydrogen-like atoms, that is, one electron atoms. Any modification of Bohr's theory, and many such modifications were attempted by Sommerfeld and others over the years, none of these modifications work for many electron atoms or molecules. No one recognized these shortcomings more clearly than Bohr himself, who was always very clear that a fundamentally new theory would be required. For, in his own words, nothing has been said here about how and why the radiation is emitted. I hope I have expressed myself sufficiently clearly so that you will appreciate the extent to which these considerations conflict with the classical theory of electrodynamics. On the other hand, by emphasizing this conflict, I have tried to convey to you the impression that it may also be possible in the course of time to discover a certain coherence in the new ideas. And that's what we will turn to next week.